In a school test, a misplaced decimal point costs you a grade. Out in the real world, a single decimal shift causes an entire structural vector to collapse. To protect our calculations, we rely on the rule of vertical alignment. We lock the place value columns together by stacking our numbers, like 75.345 and 86.691, so the decimal points sit perfectly along a single vertical axis. Adding from right to left, the thousandths column gives us 6. In the hundreds, 4 plus 9 equals 13. We write the 3 and carry the 1 over to the tenths. In the tenths column, 1 plus 3 plus 6 equals 10. We drop the 0 and push the 1 across the decimal line into the whole units. Following this vertical structure ensures we arrive at the correct sum, 162.036. These euro-cent coins represent precisely 1/100th of the note they are resting on. Because of this relationship, a single unit error shifts a calculation by 2 decimal places. In 2013, the Amsterdam City Council accidentally processed housing benefits in cents instead of full euros. The system shifted the values by 2 decimal places, turning an intended 1.8 million euro payout into a 188 million euro error. In 1983, a Boeing 767 ground crew calculated fuel weight using pounds instead of kilograms. Since 1 pound is roughly 0.453 kilograms, the pilots took off with less than half the fuel they needed, forcing a mid-air emergency landing. This risk extends to hospitals, where misreading a 0.05 milligram dose as 0.5 milligrams results in a patient receiving 10 times the intended medication. In these environments, locking down decimal placements and conversion factors is a matter of physical safety. Notation can be deceptive when measurements don't follow a base 10 system. If a carpenter builds a 2.5-foot door for a 2-foot 5-inch opening, the wood will jam against the frame. The error is in the units. Because a foot contains 12 inches, 0.5 feet is actually 6 inches. A door that is 2.5 feet wide is 1 inch larger than a 2-foot 5-inch opening. This same visual pattern appears on sports scoreboards. This cricket scoreboard shows 35.4 overs. Since an over consists of 6 balls, this isn't a decimal fraction of 10. It represents exactly 35 full overs and 4 individual balls. Treating every dot as a base 10 decimal leads to these measurement blunders. We can catch these errors early by calculating an estimation boundary. Let's look at 25.936 plus 8.202. For the lower boundary, we add the whole numbers, 25 and 8. This tells us our final answer must be greater than 33. For the upper boundary, we add 1 to each whole number. 26 plus 9 gives us 35. Our exact sum must sit between these two numbers. Pause the video and add these 2 decimals using the vertical alignment rule. Check if your result lands inside the 33 to 35 safety net. The exact mathematical sum is 34.138, fitting perfectly within our predicted limits. Running this check ensures that if a decimal point slips during your calculation, you will see it immediately. Here is a final puzzle from the textbook. Mahi is buying 0.25 kilograms of beans, 0.3 kilograms of carrots, 0.5 kilograms of potatoes, 0.2 kilograms of capsicums, and 0.05 kilograms of ginger. Because these decimals have different lengths, you must rely on vertical point alignment to avoid adding the wrong place value columns together. Align the columns, calculate the total weight, and leave your answer in the comments. Moving forward, remember the 3 core rules. Line up the decimal point, check your units, and always estimate your boundaries. These steps provide the precision needed to handle any numbers that lie beyond the point. See you in the next chapter.